Okay.
Okay, good.
All right, well, let's go ahead and get started. Hi, folks. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Program Seminar Series. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We typically wait until the end of the presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted when you're not intending to speak. Today is our third installment of a mini series where we hope to hear from one state survey each month. These talks will provide an overview of the state landslide program, including expertise, focus areas, and product types, and introduce the most pressing landslide related problems that the state faces. If you'd like to have your state landslide work spotlighted as part of this mini series, please just shoot me a message and we can coordinate a date. I also just want to add that our seminar announcements that go out via email now include a link to find our recorded presentations, which we formally started putting together in FY21 Q4. And so those are available online now. Again, that link is in the email. We anticipate about a 2-week latency or turnaround time between the transcription services and the review by USGS Digital Services. So it takes a little time to get them up there, but I do expect them within that time period. Jeff, thanks for providing the introduction today. I'll go ahead and turn it over to you.
Thanks, Matt. Well, it's my pleasure to introduce Rich Giroux today. Rich is a geologist with the Utah Geological Survey, and he's been with that group for the last 24 years, which is interestingly about the same amount of time I've been doing landslide work, and Rich and I have run across each other a number of times. And so I know he has a lot of experience on a wide variety of landslides in Utah, and will be able to really share a lot of knowledge that he's gathered over the years. Before he joined the Utah Geological Survey, Rich received his bachelor's and master's in geology from the University of Idaho, and he's a registered professional geologist in Utah and Idaho. He has a specific interest in debris flows and specifically, even more specifically, fire-related debris flows. And I really think of Rich as the authority on debris flows in Utah. And in fact, he kind of wrote the book about how to assess debris flow hazards on fans in Utah. He's currently actively involved in preparing landslide inventory maps on the Wasatch Plateau and has spent a lot of time working on a wide variety of landslides in Utah. And so it's my pleasure to introduce Rich, and I think he'll be able to give a great overview of landslide problems in the state. Rich, I'll turn it over to you.
Okay, thank you, Jeff. Oops.
And Rich, don't forget to turn off your video if you wanted to. I remember you said you might want to.
There, okay, yeah, there we go. So, Matt, can you see my first slide and everything okay?
Yep, you look golden.
Okay, thank you. Well, thank you, everybody, for tuning in, and also thank Matt. I think this is a really great series, and hopefully I'll share some meaningful things today. A lot of the state surveys, we have similar sorts of problems. So even though Utah is a very dry state, second driest state in the country, we do have a lot of landslides. So I think a lot of that is having enough steep topography, enough precipitation, and we certainly have enough weak geologic units. So today I'm going to talk about the different types, the problems, and I'd like to talk a little bit about risk reduction, where it happens and then where it doesn't, and where we're kind of just stuck in the middle, that type of a thing. So I would like to thank my co-authors here, Greg McDonald, Tyler Knudsen, and Ben Erickson. But also for Utah, it's really been everybody that's worked here and contributed to our landslide. So certainly Francis Ashland, who used to work here, he gave a great presentation a few weeks ago on landslides in Pittsburgh. And then also other people in our shop that have retired, Greg Buchelman, Bill Lund, Gary Christensen, especially Bill and Gary. They worked through the wet years of the 1980s and the Thistle landslides and those sorts of things. So, and then also we've had a lot of contributions from the U.S. Geological Survey back to those wet years in Thistle, Rex Baum, Bob Schuster. I could go on and on and on. There's just a lot of different people, Sue Cannon, Jerry Wazorek, Tom Pearson. So I could go on forever on that. So, but today on the case histories like the one I have up on the screen, I want to explain a little bit about what happened, a little bit about the geologic background of it, and then, what actually came of it in the end, because we're really, trying to reduce our landslide hazard overall. But this is actually a May 25th, 2005 debris flow on the south side of the Uinta Mountains at a dude ranch. This slide originated as a debris slide, transformed into a debris flow, and took out one of the sleeping cabins that you can see here, where all that's left of it is the roof. The dude ranch was not open at this time, but this was in 2005, they had another event from a rainfall event in the same drainage basin, a smaller debris flow. At that time, the Forest Service under special use permit was saying, you need some risk reduction here. Things went back and forth. There was some litigation. Basically, the dude ranch ceased operation and the Forest Service eliminated everything that was here. And then there's also kind of a parking area here that worked for the dude ranch and as a trailhead for wilderness. That's just used as day use only now. So that was kind of the risk reduction measures. I might also mention in 2005, there was also a debris flow into a Forest Service campground, and they've closed that campground, and it still remains closed. This is a picture of the Salt Lake Valley. This is actually from Clarence King's expedition on the 40th parallel. So Gilbert Munger was a landscape painter, but I have the question here about landslide risk. And I think all states face this in a sense that in 1869, 1870, we really didn't have much risk. There weren't a lot of elements at risk, but this is the Salt Lake Valley. Today it's totally urbanized. I mean, everything's built out, freeways. We have, you can see kind of what the high horizontal line here, the Bonneville shoreline. We have building that's encroaching up the mountainside above that. So, and we have, canyons with interstate freeways. We have canyons that lead to ski areas and ski resorts that are very congested with traffic and have geologic hazards and problems associated with those. In fact, right here, this is Twin Peaks, and I'll be showing some of the problems from several debris flows, really, but one big one in 2019 that caused problems with the highway. Just to kind of bracket your thinking a little bit, all the states have been settled and we all have landslide problems through time. Utah was settled in 1847. We can go back and look at newspaper records. We started having landslides in the 1880s, 1890s, and we'll show some examples of those, but it was really in the 1980s, and that's when we had a period of wet years back to back. We ended up having some big landslides like the Thistle landslide, big disaster. And at that same time, Utah was really starting to understand their earthquake risk a little bit better. And as part of that, at least that earthquake risk, the U.S. Geological Survey, through NEHRP funding, they founded what was called the Wasatch Front County Geologist Hazards Program. And so this was basically putting geologists in the most populated counties along the Wasatch Front, which was good. And there was a lot of great benefits that came from this. All of those geologists, those county geologists at that time, they resided in land use planning offices. They produced hazard maps. There was zoning, there were areas defined where special studies had to be done. Then they would be submitted to the county geologist and reviewed. Risk reduction measures would be implemented where they're needed. However, the NEHRP funding went away and all the county geologist programs went away except for one in Salt Lake County. So things kind of continued along and kind of progressed from there. And then in 2005 and 2006, and sometimes a little before that, Utah started having a lot of problems. We were basically getting landslides and subdivisions that weren't totally built out yet. And, in some of these cases, we actually had geologic hazards reports that deemed the area safe for building. And really kind of the long and short of it, county planners were basically accepting a signed and stamped report from a geologist or an engineer, not doing any peer review, just accepting it at face value and calling it good. And that kind of got us in trouble. And our governor at the time was John Huntsman, and he says, well, this isn't right. And so through our shop, primarily through work that Francis Ashland was doing and Gary Christensen, they started the Governor's Geologic Hazards Working Group. And through that, they really took a look at all the problems and what was going on. As you can imagine, they came up with several recommendations. One of those was, yes, we need peer review, no matter what. You just can't take things at face value. 2, yes, we need to update hazard maps. 3, yes, we need to do more landslide inventory mapping. Yes, we need more superficial geologic mapping to support geologic hazard maps. And we also need to implement geologic hazard ordinance wherever we can, as often as we possibly can. So, and then for our program here for the Utah Geological Survey, it actually allowed us to add a couple people. So I won't spend a lot of time on how our survey is organized or anything like that. You can go to our website for that. We have about 65 employees in our hazards program. We have 8 geologists and 1 program manager. And I'll just kind of leave it at that. Some of our staff works, we kind of cross over with our mapping program a little bit. A couple of our hazard geologists are good at superficial mapping, and so they'll work with the bedrock people on producing maps from that standpoint. On the left is the report from the governor's landslide or geologic hazards working group. You can look this up if you need it and see what some of those recommendations are. Another publication that is pretty popular for us, and even though we were doing this before the working group and doing hazard maps before the working group, you'll see that as well. But we've tried to make it a one-stop shopping. We have guidelines for surface fault hazard, for surface fault rupture hazard, for sliding landslides, rock falls, debris flows, ground subsidence, ground fissures, and then also the model ordinance is in this same publication. And the model ordinance is created so a community can adapt it and easily modify it, put their name in certain places and that sort of thing, just to kind of expedite getting that in place. Little bit about landslide loss planning and response, and I'm not going to brag that Utah landslides are bigger and better than anybody else's, but they were all kind of the same. But we have 34 landslide fatalities in Utah. The next bullet is not a misspelling from the other word you might be thinking of, but it's we call ourselves the State Hazard Mitigation Team. And so we meet 4 times a year. It's really a mix of federal and state agencies and employees, the Weather Service, the Snow Survey, the Geological Survey, the NRCS, anybody that works with natural hazards and problems. And it's kind of governed by the State Division of Emergency Management. I'd like also to mention that the Utah Geological Survey, we don't really have any regulatory role. So when a landslide issue comes up, it can come to us directly as a phone call or from the State Division of Emergency Management. But another thing that's very clear in our role as a state survey, it's actually set in state code, is that we are required to assist local government. So anytime a city or a county, they don't have geologists on staff and are grappling with a geologic hazard problem, then we will go and assist them from that standpoint. And so we work closely with city and county planners and then also emergency managers. So over on the right, I want to talk a little bit about the state of Utah and some of the areas that I'm going to show you some examples of Utah landslides. So my pointer right here is right about where Salt Lake City is at. And we have a population of 3.1 million people. And that basically 90% of those people from Ogden up on the north to Provo down here by Utah Lake on the south, 90% of our population lives there. So most of our population lives on the Wasatch Front. But we're growing very quickly. In the last 10 years, we've added 500,000 people to the state. So we see spillover into the valleys to the west and into the back valleys to the east. So we're growing. I know other states have more people and more problems and maybe more elements at risk, but these are just some of the issues that Utah's grappling with. In terms of areas that I'll show, we'll talk a lot about the southwest corner of the state here, the St. George area, the Cedar City area, Zion Park, some of the hazard mapping that's been done there. And I say central Utah and the Wasatch Plateau, that's this area right here. And Utah is really kind of divided up, you know, kind of north-south, kind of this whole western part of the state, that's all in the Basin and Range province. You see all these north-south trending mountain ranges. Over here in the southeast part of the state, that's mostly Colorado Plateau country, but we do have some quite, you know, some fairly high plateaus for Utah, plateaus that range up 10,000, 11,000 feet. So we get a lot of snowpack and a lot of precipitation on those. And then kind of the northeast corner of the state up here is all kind of what you call Middle Rocky Mountains. This big east-west range here with the white color on top, that's the Uinta Mountain Range. And that first slide that I showed of the Dude Ranch guest cabin that was destroyed by a debris flow is on the Uinta River, and that's about this area right here. Of course, this large lake right here, this is the Great Salt Lake. This is the remnant of the former Lake Bonneville, a large Pleistocene lake that occupied a lot of the north part of Utah and the west part of Utah. In terms of, I will show examples. I mentioned the St. George area, the Cedar City area, the Wasatch Plateau. We'll have the Thistle landslide. It's just kind of over here east of Utah Lake a little bit. I'll have several examples along the Wasatch Front. Also some up here by Ogden, where we have continual problems along a bluff and a canal corridor. In terms of looking at our current landslide inventory and hazard mapping, I mentioned the St. George area, the Utah Geological Survey. Boy, it's probably been about 25 years ago. I really made a decision. It's like, no, this area is really growing like crazy. It's a very popular retirement area. And so we made the effort to go and do geologic mapping in this area, and then also hazard maps, derivative maps from those hazard maps. And that's what you see in this area. We've also produced hazard maps with the National Park Service at Zion National Park, and also over here in the Glen Canyon Recreation area, and then also hazard maps. These are quadrangle maps up around the Cedar City area. A lot of the landslide inventory mapping I've been working on are joint projects with the Manti La Salle National Forest. That's this area right here along the Wasatch Plateau. These long, little skinny, slender lines are the mapping that our fault mappers have done recently with LiDAR on mapping active faults in the state of Utah. And the area up here, these are other hazard maps, quadrangle maps for hazard maps that are in place. Probably our most famous landslide, if you'd like to call it that, would be the Thistle landslide. It happened in 1983. The loss values vary, but most of them come up with something over or under slightly around 500 million. This number in 1983 dollars probably makes it the most expensive landslide disaster in the US. There were no fatalities. Most of this dollar amount is really a function of losing a railroad, losing a town, and losing a major highway corridor that would come into Provo, Utah. So you can see here, the Thistle landslide is, it's right about a mile and a half long. And it's ran out and into Billy's Mountain over here. It's actually sliding on the Triassic and Kara Formation. But when you have this geometric configuration in the valley, it allows you to really impound water at a significant depth. And so this is Lake Thistle. The highway was relocated to the left out of the field of view over here. This is Billy's Mountain. The railroad tunneled through Billy's Mountain, and then there was also a tunnel underneath Billy's Mountain to drain Thistle Lake, and the Spanish Fork River runs out through that tunnel to this day. Thistle is it's still active. Parts of it still move, just kind of depends on the year, that sort of thing. So I wanted to do just kind of a relative scale comparison. This is not to brag that Utah has some large landslides or anything, but we have some that at least get us on the scale. So on the very far left are really large events like Mount St. Helens. Then there's the Bingham Canyon mine, even though it's a man-made landslide, was still a large landslide. And then the Gravant landslide in Wyoming, the Frank slide in Alberta, Canada, the Madison Earthquake Lake landslide by Hegman Lake, Montana. And then we start to get into some of the Utah landslides that are, right around the 20 million cubic meters volume. So here's the Manti landslide, that's Wasatch Plateau in central Utah. Thistle that we just looked at, I'll look at 12 Mile here in just a little bit, and then Oso here for comparison, Oso, Washington. So let's look at 12 Mile Canyon. We have these large scale landslides, and they're just, really dramatic transformations of the landscape itself. And then the landscape itself is always trying to readjust to these big landslide movements. So here we have an image from 1976. Pre-existing landslides may not be that apparent. Then we have the 1983 12 Mile landslide right here. There was also a debris flow that came off the end of this landslide that flooded out and damaged the Pinchot campground a couple miles down below. And then here's some imagery in 2000, and we get yet another landslide, the 1998 North Fork of Coulee Creek that comes in. This part of the landslide, the upper part above this knob, you see in the valley is about a mile in length. These are a couple of Google Earth images, but I just wanted to kind of move through these quickly because they show the scale and the impacts on the environment, and then also the impacts on water quality. So here's the 1983 12-mile landslide, and then this is the North Fork of Coulee Creek coming in. This is looking down the South Fork of 12-mile creek with a 12-mile landslide, then this is the North Fork of Coulee Creek coming in. So the streams are continually eroding sediment out of these landslides and taking it downstream. The water is used for irrigation. The farmers that use the water have had a lot of problem with suspended settlement. They have to create extra settling ponds to use the water. That would be the risk reduction that has been done to date. This area here is a difficult area to work in. It's all a roadless area. I might also add, I think Rex Baum he worked on a couple of these landslides a little lower down. There were two other landslides across from each other that were impinging on the creek, threatening to block the creek and create another situation like Thistle in 1983. And the one on the north side, the Twin Lake Reservoir landslide, did take out the road. I wanted to show you this picture so you can see these landslides in kind of a full-scale landscape perspective. This is the Slide Lake landslide. It's kind of the classic, it's got the hourglass shape and that sort of thing. But it's about a mile long. But it goes to show you the scale of some of these landslides. It doesn't really matter which drainage you're in. Almost every drainage has one of these very large landslides, and a lot of them have historic movement. This particular landslide, you can get up here in the waist of the landslide or the track, and you can actually, with imagery, you can see the large boulders march down the landslide itself. Most of them have a little component of back rotation in the head, and there is a lake at the head of the landslide. And these are very good because they capture the snowmelt runoff and provide a continual plumbing source of water for these type of landslides. This is another landslide that was threatening to block the creek down here, Seeley Creek, in 1983 as well. Now I'd like to move on and talk a little bit about some of our rockfall problems and our rockfall issues. The town of Rockville is about 5 miles south-southwest of the South Entrance to Zion National Park. This area was built before we did our hazard maps in this area, but the red shows the high rockfall hazard area. And probably the most important thing to note here is like our chronology of rockfall events. We start in 1976 and we end here in December of 2013. So all of these events kind of help us calibrate or validate our hazard mapping from that perspective. But this is also an example of where you have a hazard, you get a rockfall, it hit somebody's house or missed a house, and then everybody just goes back to the pre-event risk level. And they're still living with this issue. And it's difficult because long term here, when you see some of the subsequent photos that I show you, this type of development probably isn't sustainable. It may work for a few decades or something like that, but sooner or later you're going to get a rockfall event. It's going to cause problems. And here, this is the actual setting in Rockville. We have the resistant Chinnerup conglomerate over the South Moen Kopi Shell. 7 major rockfalls in 38 years, 6 in the last 13. You can see the size of some of the rock class down in and around the houses that have been built here. This is a 2010 event, rockfall that comes off. It hits some of the rocks lower down on the slope, breaks apart into other rocks. This is a class that broke off and rolled through this part of the house, which is underneath this green awning right up here. So it's just kind of a continual problem, and it never really goes away. Here's another house built in and among the large rock class. The key here for the subsequent picture is to watch the gable roof on this house. So here it is, destroyed the house, garage, car, killed 2 people. This was likely a freeze-thaw event. This was December of 2013. So just a sad situation and just an area where you have continual problems. I want to move on to the St. George area and talk about some of our hazard mapping and some of the success stories with that. So this is a hazard map over here. The red shows the high hazard for rockfall. Some of the subdivision was already built. There's pre-existing development when this went in. Then we had a rockfall event here. You can see in this inset picture, this is a large class to Kayenta sandstone that luckily stopped right before it got to the house. This is the house that's circled in the white right over here. So these type of events, though, really raise the awareness of land use planners and people that work on, I think this is a hill slope community here. So But I wanted to show you a couple of examples of subdivisions that have been redrawn or where risk mitigation is recommended and necessary before building. So our maps are hazard maps. They're really red flag maps. They just force a detailed study. This is a case where there is a site-specific analysis, and then this dashed line is where either a rockfall berm or a rockfall fence is necessary to protect the development, to protect the subdivision. Another rockfall in a high hazard zone. This is proposed development right here, the Cottom Cove subdivision. This is in St. George. You can see some of the faults here that are mapped as well. It was flagged by the Hillside Review Board. And this is probably one of the most important things we do in addition to producing good quality hazard maps. And that's the ability to communicate that hazard and those maps with the planners, the developer, the city officials, the geotechnical engineers that are involved, and the hazard geologists that are involved. So that's really critical. We can do the best and have the best maps, but if we don't communicate that hazard to the decision makers, we're really not going to be successful in reducing the risk of these rockfall hazards and other landslide hazards as well. So this particular case, I think you get the picture here, the number of rock falls that have come out of this cliff band, this outcrop band up at the top of the slope. In this particular case, after the site-specific assessment, 12 lots were eliminated and then other restrictions were imposed. But when you look at this map and the topography, it's kind of ridiculous how high they had pushed the lots and the lot boundaries up onto the slope. So it's not just southern Utah that we have rockfall problems. I wanted to show you a couple from Provo. This is Y Mountain. This is just north of the Brigham Young University campus in Provo. And this is a case where we get a rockfall source that's a long ways away. In this case, the rockfall source is like 2,600 vertical above the house and slope distance about a mile. So it's not that apparent, even though there's rockfall class in and among the houses, but to a lot of homeowners, they don't realize that the level of danger that they're in. But in this particular case, this is the Deseret limestone. It's a Mississippian limestone, and it produces these, as you can see in the lower left, these roughly equidimensional class, and they really just don't fall apart unless they hit another rock on a slope. And this is a smooth colluvial slope, so these rocks make it all the way down down to the bottom. So you can see the rock kind of hiding above the garbage toter here. And this is a guest house that was impacted and eventually demolished. This is another house, 2 houses to the north. This gives you a little, the upper right, upper left, we need to go counterclockwise here. A little bit better what the cliff band, what the source looks like up here, where these big blocks of Deseret limestone peel off. This rockfall class was bouncing down the slope, bounced over this chain link fence, hit in the backyard, bounced up into the house, bounced through the outside and an interior wall of the house, and then on its downward trajectory, it went into the living room floor and fell all the way through the living room floor into the garage down below. And that's what you see here in the upper right-hand corner. And another one of these roughly equidimensional rockfall class. Wanted to go and look at some landslides directly east of Cedar City. I think every state has these, a corridor where you have a highway and you have really problematic conditions. Here we have the the Straight Cliffs sandstone, the cliffs up here. Under that, we have the Tropic Shale and the Dakota Formation that are causing these sliding type landslides. 1989, a landslide that closed the freeway. The landslide was regraded. They've had pretty good luck with this. Some landslides in the mid 90s over here on the viewer's right. 2009, a big rockfall event that came down onto the road. I'll show you some photos of that. And then again in 2011, another sliding type landslide that took out a good part of the road. These adits or old mine adits are within the Dakota, there's some coal seams, and that's the reason for those mines. This is a photograph of the 2009 rockfall event. You can see some of the sizes of the class down here in the lower left. University of Utah Seismic Station picked up a magnitude 1.7 earthquake, and the timing of that that they picked up, and then also with the motorist that came up the road, couldn't get up the road and then went back out to get cell service and call the sheriff's department. Fits that time constraint pretty well. And then the 2011 landslide took out about 1,200 feet of roadway, I forget exactly. I think it was, maybe about 9 months to a year before they got the road open again. They did as much stabilization as they can. Over on the right flank of this slide, they're still having problems and the landslide is still moving. I'd like to move on and talk about a different type of landslide, rock avalanches. We don't have as many of these as we do of the others, but they're around there. I mean, we have 5, fairly sizable rock avalanches within about 40 miles of Salt Lake City. This Kelsey Peak rock avalanche is about 30 miles south of Salt Lake City. This is a big dip slope failure. If you look over here on the left, you can see the rocks dipping. This is the Butterfield Peaks, the Pennsylvanian formation. This formation does have some argillic beds and some shale beds that might be the case for the failure. Here's some of the bedding failure surface right here. And then in the inset photo, we've been lucky enough, Jeff Moore at the University of Utah. This is one of his graduate students, Brandon Quirk. Jeff and his students have been working on some of these rock avalanches to get some dates on some of them, and in northern Utah, and then also down, Jeff and his students have been working on some in Zion National Park as well. Utah debris flows. So we've had debris flows in Utah basically since the state was settled. So 175-year history, late 1800s, we start seeing events. We had a lot in the 1920s and 30s, and a lot of this is from overgrazing. And if you look at the landscape at that time, it was no different than what we see now following wildfires. The landscape was totally denuded, intense thunderstorm rainfall, the same debris flow triggering mechanisms that we get today off of burn areas. So, and then historically, we can move up into the 1980s. I mentioned these were the wet years, like when we had the Thistle landslide, the 12-mile landslide that I showed you examples of. We had a lot of floods. We had a lot of snowmelt and snowmelt type debris flows during this period of time. The period of time in 2000 to 2005, we were in a drought, kind of where we are right now. So we had a lot of fires, and this was when Sue Cannon was doing some of her work on the early phases of the USGS post-fire debris flow model, which is a great model. But Sue and her crew came out and worked on some of the Utah debris flows, and we worked together on this, which was quite enjoyable in that sense. Fatalities, we have 15 fatalities from debris flows. 13 of those fatalities are both in campgrounds in 2 different events, and they happen at night. And they just go to show and reinforce how important it is to get people out of harm's way in the middle of the night. You just really don't have the awareness and the ability to evacuate as fast as debris flows move. The upper right's a 1923 photo, some old Model Ts, if you can see those in the background. This is up in Willard. Risk reduction for this particular event was a large debris basin. The lower photo here is from a 1964 fatality in a campground in Sheep Creek on the north side of the Uinta Mountains. This particular event killed 7 people, and the risk reduction here was to eliminate the campground. There is a picnic area here and a memorial, and in the picnic area it just functions as a day use only facility. I'll talk a little bit about fire-related debris flows. We do work on bear teams from time to time, but I said most of the time we work with our state hazard mitigation team. Seems to be a little bit more effective way for us and to getting information out and working with the other parties that deal with fire-related debris flows. But this photo shows our hazard, very steep slopes up above a community. This is Provo. I'll show you some examples of what happens when debris flows initiate on these type of slopes and run out onto the alluvial fans down at the mountain front. Impressive for overland flow at times, just the size of rock class that can be moved with intense thunderstorm rainfall. You can see and kind of understand a little bit of how the triggering mechanisms work, for these fire-related debris flows. And the bottom 2 photos are just recent photos from this year from the East Fork fire. The road was closed twice, a Forest Service County road that goes to Upper Stillwater Reservoir, very popular camping area. People were trapped for a short period of time until they could get the road open again. So, and there's now also a Miners Gulch campground. The Forest Service closed the campground in that area as well. So, what happens when debris flows come out onto alluvial fans and there's no debris basins or other protective measures? So Santaquin's a good example of that. This was a fairly large, for a fire-related debris flow, right around 20,000 cubic yards. There's another lobe off to the left that you can't see here. But it goes to show you their squirrely nature, how they don't directly go down slope. This would have gone straight down this road right here, but they kind of pulse and avulse all over the alluvial fan. This is an example of some of the type of damages that we see. We're just easily, house walls punched out. Of course, the routine statement, don't sleep in the basement. Here's a window well with mud and debris going into a house. So. Campgrounds, this is back to Santa Clemen's just south of Provo, Utah, that previous example. Lower Bridges Campground, we've had 3 different flows in here following the Sealy fire, but it just goes to show you how prone campgrounds are. This campground is now permanently closed as well. This is my picture to see if anybody's still awake. And the question is, what's wrong with this picture? And I think if you take a close look, you'll see that the creek isn't flowing under the bridge any longer. So this is a case where we had a debris flow, a fire-related debris flow out of Mill Canyon. It totally filled up Huntington Creek and then diverted Huntington Creek around the bridge. And now I'd like to talk a little bit about debris flows that are not triggered in fire situations. This is actually a rainfall event in the summer. If you remember in that painting of the Salt Lake Valley, I pointed out Twin Peaks. So this is that same area. So this is only from where you sit on the road here, you're only about 2 miles from the Salt Lake Valley, but it deposited a large amount of sediment, 10 to 12 feet here on the highway. It was intense rainfall. There were also floods. This is State Route 210. It leads up to Snowbird Resort and then also the Alta ski area. The governor ended up declaring a state of emergency. We had 35 stranded vehicles along a 4-mile length of highway. This is a case where social media was good and bad, had as many false reports as good reports, major damage to the highway and utilities, multi-agency response, and not the first event. So this is like, we had one in '69 we're aware of, also 2010 and 2013. So not the first event. This is looking at the canyon. The previous photo was looking over here on the left at Lisa Falls. This is Little Cottonwood Canyon. It's a very narrow, steep, U-shaped glacial valley. Geology-wise, all the white rock here is the quartz monzonite stock of Little Cottonwood Canyon. It's intruded up into the Precambrian Big Cottonwood Formation. This is Twin Peaks that I showed you on that landscape painting previously on one of the previous slides. So steep drainage basins, a lot of relief. There's 4,600 feet between Twin Peaks, a little over 11,000 feet by the time you get down here to the apex of Fan at Lisa Falls. Very steep rocky drainage basins, very prone to rapid runoff, thin colluvial cover, loose rocks, easily incorporated into debris flows to make it onto steep fans. These fans are 11, 13 degrees on the upper parts to make it to the road, to deposit sediment right on the road. So other thing, there's one small rock avalanche deposit right here. This is the White Pine rock avalanche deposit. Now I could go in and look at Canard Gulch, not quite as steep as Lisa Falls, but still had some impressive debris flow that came out. This is one of the photos where you just get lucky. This is a natural gas line. I remember after the briefing at the Emergency Operations Center, the county sheriff came up to me and he couldn't believe how lucky we were that we didn't have a problem with this. I think if you remember the Montecito, the debris flows that were there, I believe it was in January of 2017, there was a fire from a debris flow that damaged a natural gas line. So we were very, very lucky in this particular case. We're off the cathodic protection, but it didn't hit it and spark it. There was no way to get a fire truck here. Road was closed 2 miles above and about a mile and a third down below, that type of a thing. To make matters worse, there's another campground here about 300 feet away from where this gas pipeline was exposed. So this is looking up Canard Gulch, milepost 8 on the highway. This event moved some really sizable rocks, 4 to 6 to even 8 feet across. A couple geologists for scale, Ben Erickson on the left, Adam Hissock on the right. But just impressive. Everything is still, this is an incised channel on the alluvial fan, everything's staying in the channel, but impressive, really moves some big rocks. And I think you can see some of the gradation here along the right channel bank or in the viewer's left. If you look at this rock face back here and this rock face back here, this is a 2013 event. And then this is a 2019 event. But I think you can see that there's really a lot of material that's accumulated. So in this case, we came in with our drone, did structure for motion, generated a DEM and compared it, did some topographic differentiation from the 2006 LiDAR. And it showed anywhere from about 2 to 4 meters of gradation. So, and also another photo, people don't understand, you know, it's not water that's moving those, it's really this viscous mass. So this is what that material looked like on the inside of the deposit. So just a couple fun snow photos here, snowmelt landslides. I'll just show one, but we get a lot of these, especially when we have above normal snowpack winters. Over on the left, a big snow drift supplying water, thin landslide, but everything breaks apart and the snowpack comes down the hill with it. On the right, a snowpack that was over the toe of a landslide, and then the landslide reactivated and actually took the snowpack and tipped it vertically. If I was a day or two late, I wouldn't have been able to take this picture. Lower left, just nice tension cracks formed in the snowpack up above a landslide. All the snowpack didn't need to melt in order to trigger the landslide. And then lower right, just a nice fresh landslide scarp during snowmelt. I did want to profile one. This is the same highway that I looked at before with the problem area down lower, east of Cedar City. This is the main road going up to Cedar Breaks National Monument. You can see here a large landslide is released. Some of the snowpack is still in place. And it's really this slide on the left, there was only the lower landslide. There was a pre-existing landslide, but only the lower part released. It did release into a very steep, narrow channel and transformed into a debris flow. That debris flow made it 1.6 miles all the way out to the highway. So this is one of these hazards that starts a long ways away from what actually ends up being at risk from that perspective. So but you can see here the middle photo, just taking out a swath of trees that are 1 to 2 feet in diameter. And here's the actual landslide impacting the highway down here. In this particular case, even though we don't have a lot of data, we try to go to and use the nearest snowtail site. This is about a mile away. This is the Webster Flat snowtail, but it gives you some idea of the snowmelt rates and the water inputs into potential triggers for landslides like this. So this is just a graph of the snowmelt at this snowtail site. We started with an initial snow water equivalent of 33 inches. The blue line shows temperature, warm and cold periods initially, but it's really the kicker here at the end. The orange are basically showing the loss of snowpack from the snow pillow in inches of water per day here in terms of what's lost. But at any rate, for the last 14 days, we lost 1.5 inches of water a day. So right around 21 inches of water. So that's a lot of water to put out in any landscape. If it rained 1.5 inches a day, in Utah, people would go nuts. We're a fairly dry state, but in this case, you certainly see that in terms of triggering landslides, and you also see it as a stream flow response as well. I'd like to move back up to northern Utah, talk about an area where we have continual problems. I think all states have these. Your little bluff that's high or low, but just very weak materials. This is Ogden would be just off to the left. This is about 30 miles north of Salt Lake City. This large area here is the Weber River Delta, a delta that formed in Lake Bonneville. As Lake Bonneville receded, the Weber River cut bluffs on either side of the valley. And I want to look at some of the landslides, 3 along this side of the valley, 1 on the left. These are associated and show some secondary hazards with the canal. This big runway here would be Hill Air Force Base right there. But I do want to talk a little bit about the Davis-Weber Canal. It was constructed in 1884. 6 miles lie along the bluff. Originally agriculture, irrigation, now mostly landscape. We have urban encroachment from above and below. Had landslides reported as early as 1898. These landslides used to impact agricultural crops, but now they impact urban development. We have both landslides and landslide complexes. 49 landslides are mapped along the corridor. I might mention this was done by that county geologist program, that initial influx of NEHRP money that came into the state. the canal crosses 25 landslides, and then 23 of the 25 are active, have shown historic movement. So it's definitely a problematic area. The canal companies take risk reduction measures. They stabilize some landslides, but for the most part have gone away from an open canal and putting the canal into a box culvert. So it's a much stronger conveyance. This is a 1999 canal breach. We're not certain if this was a landslide or not, since all the evidence is eroded away. You can see some of the impacts here. I think there was fairly significant damage to about 15 to 20 houses, sediment flowing into houses. You can see the sediment depths here, about 4 to 5 feet at the max, and then trying to open a road up right here, which gives you some of the sediment depths as well. I think here it was about 67,000 cubic yards was what was eroded out. You can see the canal right here. I think the canal ran for about 3 hours before it was out of water. Moving a little further up, a 2005 event took out a barn, no water in the canal, part of a larger complex. It was stabilized for around 3 million. This is the upper part of the slide. You can see it here. This actual landslide was actually instrumented. The landslide took out an inclinometer that was in place. The upper photo is important for us, especially when you have these rapid earth flows. This run out distance is important for us when we go and do hazard maps in this area. Another event in 2006, a year later, a pond up here, the drain malfunctioned, allowing the pond to overfill, saturate the crest of the slope up here, and then a landslide triggered, went over the canal at this point, which was in a box culvert, no water in the canal, but impacted the back of a house, and a child was injured in this particular event. No risk reduction at this site. The canal company's happy with their canal and a box culvert, and just problematic land ownership or other things to do any sort of risk reduction. And 8 years later, we had 2 other small landslides. Moving across to the other side of the valley, one of our more recent landslides started in 2017. Repeating drone flights shows some of the enlargement of the landslide. 3 of the houses were evacuated, and those are now torn down. There's also a voluntary evacuation on one of the other houses, but just continually problematic. The green shows you some of the run out. This always has water running out of it and some of the sediment deposition down below the landslide. Switch gears just a little bit, but another problem, this is just south of Utah State University, Logan Bluff. A landslide that killed 3 people. There used to be a house right here, but this idea of a secondary hazard, this lower left-hand photo shows you water right after the event running out of the canal, which sits right here. So really complicated the search and rescue efforts in that particular case. Look at a couple of other urban landslides and some risk reduction measures that have been done. This is in Layton, Utah. This is also Weber River Delta or Lake Bonneville sediments that are failing, a before, after. In this case, 6 houses were involved. 3 houses were successfully moved off the landslide. 3 of the houses weren't, and they were demolished. One of the risk reduction tools the city used was to place a notice on a title, basically stating that you couldn't buy it without knowing, or at least having been informed that the hazard was there. This was a landslide area, and it needed to be stabilized before it was built on. The city has also been able to buy a couple lots here to use as a future trailhead and a future trailhead parking lot. Another landslide, we get these, they go on forever. I think our shop worked on this one for 14 years. Spring Hill Drive, a very slow moving landslide, very low angle, about 13%, 7-8 degrees. Real slow mover. Eventually we had a FEMA pre-disaster mitigation grant that the city was able to obtain, $2 million. City matched it with $600,000, I believe, and then 11 houses were bought out. So this is now the subsequent use is the Spring Hill Geologic Park, and we kind of have the humorous headline, "Destructive landslide turned into a tranquil geologic park." And one of the interesting things about this landslide was it's within about 10 miles of every television station in the Salt Lake Valley, so it always got a lot of television coverage. If they needed a landslide, they would go out there. Photo on the right, this was a GPS survey we did with the city just to ensure what parts of the landslide were active and not, that helped on the home buyout. Parkway Drive, another one in North Salt Lake, kind of an example where you have an improper investigation of a landslide. The slope is 200 feet high. The main scarp is 60 feet high. This is a 2014 landslide. The deepest drill hole was only 30 feet. So they really didn't evaluate the slope. They missed the underlying tertiary volcanics and volcanoclastic sediments, the same bad actor in Spring Hill Drive landslide I showed previously. This landslide then kind of went into litigation battles between this covered white awning as a tennis court area and then a developer and a development. The landslide was regraded, I guess you would call it partially stabilized, or an attempt to that. It was never really stabilized. We continued to do GPS monitoring with the city. It continued to move. The drainage and everything was disrupted. Eventually, they settled on the litigation end of it, and they've gone in and regraded the landslide, put in additional drainage, and then done some buttressing. So this is an interesting landslide as well because Francis Ashland, back when he worked here, right in his tennis court area in 2005, he saw some initial movement. So this might be a case for progressive deformation over a long period of time in order to get the failure. Another one of our kind of unique landslides, Francis Ashland started working on this when he was working for us, and we're now working with him on it at the USGS. But this is the Meadow Creek landslide. State Route 9 is the main entrance, or the east, I shouldn't say main, the east entrance to Zion National Park. You can see here some of the headscarp and then the landslide itself, some of the vectors right here. I guess from Francis's standpoint, this would be kind of his research into slow-moving landslides in very dry climates. And it's a dry climate, but you really have to know what's going on with the groundwater inside it. So this upper right photo here, a recent asphalt patch on the current highway, but more importantly, the old highway that was abandoned in the 60s. And this area right here, I think you can clearly see some of the offset of the pavement of the old highway. I think it was abandoned sometime in the 60s, and then also here as well. The lower right, this is the bike race, the Tour of Utah that they have in August in Utah, but you can see the up and down of the road or some of the wonkiness of the road from that perspective. And then just kind of the final landslide I'm going to talk about a little bit here. This is the Bear Wallow landslide complex. This is the Snow Basin ski resort and ski area. The town of Ogden would be just over on the other side of the range crest here. We started doing work on this when Francis Ashland was here, started doing long-term GPS monitoring. It's a very slow-moving landslide. Parts of it you wouldn't recognize as moving if you didn't have GPS data. So right now we have about 12 years of GPS data on this landslide. The most active portions, we have about a meter, meter and a half. Other portions, much less. Other portions, not at all. And in addition to doing the GPS monitoring, this is one of the landslides that we go out and measure peak snow water equivalent on it every year, just to try to get a handle of that and what its effects are on the movement. When we have above normal snowpack or more snowpack, we do see more movement. So, and just a final parting comments. I think it's very important to map and inventory landslides. 95% of all the landslides we work on here at the Utah Geological Survey, or even more, are pre-existing landslides. So if you have those landslides mapped and you get that information out through published landslide databases or maps, that information is out there. So it makes it harder for people to build on them. It just gives them more awareness of what's out there in that sense. Another thing, you always have to educate public officials. They come in and out of the office. It doesn't matter they're at state government or local government levels. It's always something you have to do. Same with planners, same with the public. You need good information on your website. You need information out there. You need to communicate the information of your hazard maps. So having good information and outreach is really critical. And then also implement geologic hazard ordinance. The more of those that you get in place, just sending things through the process really helps on risk reduction. We kind of work in a funny business in the sense that we only hear about the bad problems. When we have success and we do risk reduction and that's taken care of and we never have any failures in that subdivision, we don't really hear about those. So it's kind of odd, but you know, implement the ordinances, run things through the process and get your risk reduction done. And then just a couple final bullets. Our objective, you know, reduce risk to life, property, infrastructure, and reduce economic loss. We're certainly not against development, but we just want, you know, wise development, you know, to build economically sustainable, hazard-resistant communities. So, and just one final slide. This is my contact information. So if you have some questions on this or anything that I've presented, feel free to contact me. And this is the final slide. This is Toto, our landslide dog. So that's all that I have, Matt.